Okay, thank you. Thank you, Chairman, and I'm very honored to be here to introduce our project. The title is Large-Scale Numerical Simulation of Earthquake Generation, Wave Propagation, and Soil Amplification. And we are collaborating with Earthquake Research Institute with the University of Tokyo. So our project started from this year, but previous project, one of the 9 priority issues to be tackled by using post-K computer. And our related project is development of integrated simulation systems for hazards and disasters caused by earthquakes and tsunamis. And we developed on simulation codes on K computer and for the preparation of supercomputer Fugaku. And in earthquake disaster assessment, currently, basically the empirical relation is used for the estimation of the disaster from the relation between the attenuation relation in the distance and the index intensity, or relation between index and damage. And this called fragility curve, and we get this empirical relation from each disasters like Kobe earthquake or Tohoku earthquakes, and then we estimate the relation. But it's not, of course, it's only empirical, and it's not applicable to other places. It's not general. So in the future, we'd like to go to more scientifically rational estimation for earthquake disaster. So based on the simulation of earthquake and tsunami and also disaster. So the aim of the previous project is to develop simulation-based disaster assessment system with scientific rationality. And in that project, we have 2 teams, and I'm the sub-leader of this part, physical simulation group, and another group was social simulation like evacuations or traffic simulations or economic simulation. But in our subgroup, we developed a code for earthquake generation, earthquake scenario simulations, and strong ground motion, and also cluster deformation simulation, and then site amplification for evaluating the building shaking. And these are based on the FEM code, using FEM code developed by ERI, Professor Ichimura's group. And also the cluster deformation, if it's occurred beneath the ocean, and then it's caused tsunami generate, and we also simulated the tsunami inundation also, and structural damage. In that project, the main part of the simulation code is for the FEM seismic response analysis by Professor Ichimura's group, and this is one example that from the presentation SC15 Golden Bell Award finalist presentation and simulation used K computer. This is for the Tokyo city around Yamanote line area, 10 kilometer to 10 kilometer, and thickness is very thin, about 300 meters, but it's very detailed structure is included, only topography and also the underground structures. And then we divided these this model to I'll show you the very detailed topography is introduced, and then it's divided into the many pieces to calculate on the K computer. this is 400,000 elements, and each one has a 1.6 million degree freedom and 80 partitions. And then we get the displacement on the surface. You can see the very heterogeneous distribution based on the depending on the underground structure and also topography. So we can calculate this very. It's up to 10 hertz. We confirm the numerical convergence, and we also calculated using the result of the ground motion, and then we also calculated the structure shaking like that. It is not a 1D structure, but 3D structure for each buildings or houses. And then we can estimate how it's different for each position. And then we can get how it's different at each buildings. And then we also can calculate the strain distribution underground. It's very important for the gas pipeline or other infrastructures. Okay, that's already achieved in the previous project. Okay, and based on such achievement, very large-scale simulations, the background of our new project, this project using Fugaku supercomputer, is that the government, especially the cabinet office, disaster management, this is responsible for national damage estimation. They needed to improve the estimation method for long period ground motion evaluation. That is very important for the estimation ground shaking of the very high, very tall building, and also highway structure and so on. And so very large scale analysis method we've developed is much their necessary and their needs. So we proposed a project and started from this fiscal year. And in our project, very small groups, only 2 institutes, research institute and other collaborative organizations are included. And our goal, there are 2 main purposes of our project. One is application of the development simulation course to earthquake and tsunami damage prediction method, aiming for the formulating damage estimates by the government, especially cabinet office, Japan disaster management. So we aim to for applying simulation course. I already showed for the long period seismic ground motion analysis, and also tsunami source estimation by the government. Then for that purpose, we make necessary improvements to develop simulation codes in cooperation with national agencies. The Cabinet Office Japan. And we develop a computing platform and construct for the construction and civil engineering companies. We'd like to provide they can to use the same framework of earthquake and tsunami damage prediction as using by the government. Actually, now the government calculating simulation codes, and different codes or different models are used for the same position or very near places to use different codes or different structures. So, of course, different results estimation and damage estimation. So it's not good. So we'd like to unify the estimation for the government and also local government and or companies. And we, or JAMSTEC will mainly this application, and for the ERI group, they developed the simulation codes, and they improve their methods for the simulation code for applying for the Fugaku. And as a collaborative organization, Cabinet Office and also other institutes or R-CCS group also, and also for the construction civil engineering companies, Osaki Research Institute or Kobori Research Complex, Taisei Corporation or Tokyo Electric Power Services and Tokyo Gas. They will use our codes to estimate the damage ground motion. And we developed 3 types of simulation codes. One is FEM codes for the static deformation, large-scale deformation code. That is important for earthquake generation or tsunami generation initiation calculation. And we will provide this to the computational seismology and geodesy community. And the main one is EFFM. This is a simulation code for long period ground motion simulation. This is we will use for the Cabinet Office long period ground motion calculation. And another one is like that is a nonlinear soil amplification code, and this is used also in the SC15 movie in the that is use this soil amplification simulation code. This is important for earthquake engineering infrastructure for the like Tokyo Gas or Tokyo Electronic Company. And in this year, we from the first fiscal year, we have improved the evaluation of long period ground motion caused by the Kanto earthquake. That is now the Cabinet Office are currently testing to improve the evaluation of long period ground motion by introducing the latest ground structure model. This is part of the Kanto area, as you see that the Miura Peninsula. This is the western part of the Kanto area, and this is the bottom layer of the structure. Such a complicated structure is included in the calculation, and we will calculate this long period ground motion simulation in the next fiscal year. We are now preparing for the calculation. And we also, I'll introduce development of large-scale analysis method suitable for Fugaku supercomputer. I will introduce two research results by ERI Ichimura-san's group. One is a research poster, SPIA SC20, fast scalable implicit solver with convergence of physics-based simulation and data-driven learning. And another one is a fast scalable iterative implicit solver with green function-based neural networks. So as seen here, the data-driven learning or neural networks. So HPC and AI or data-driven is combined in their softwares. So for smart cities, controlling city based on real-time data for high efficiency or computer modeling, the high-performance computing is expected as key enabling tool. Disaster resiliency is a requirement, however, not established yet. This is an example of the Tokyo Station District. And the point is that the fully coupled underground and above ground and underground earthquake simulation is required for resilient smart city, and this is very difficult, challenging point. That as I showed the movie for the very large area, Tokyo Yamanote Line area, that's very wide, but comparing to this, this is very not so wide area, but the simulation I showed before is not coupled simulation, only the ground motion calculated, and then structure shaking is calculated separately. But for the smart city simulation, we need to couple the structure, underground structure, and also ground shaking. So this is required for the calculation, but it's very high cost simulation to combine such structure and also underground coupling. So Ichimura-san's group introduced the combination using data analysis to solve this problem. And this is the model showing the underground structures. This is underground structure, buildings layer and soft ground layer, medium ground layer, and hard ground layer. And we calculate all these structures and solves simultaneously. And so we develop to calculate this. We develop a surrogate model for physical simulation. This learns the convergence process to higher order modes by data-driven analysis. So using the results before the current time step. So using the simulation result for the previous time steps and learn, and then to use the learned information for the convergence process in the current time step. And then we can improve the convergence in the simulation. And also the point is that the accuracy is the same for the usual earthquake-based simulation-based modeling. We only use the part of the convergence process. We use data-driven analysis. And I'll show you the simulation results for the fully coupled ground shaking and also the underground structures. And this is the model with a large degree of freedom at Fugaku for this is not full, but the 2000 nodes of the Fugaku supercomputer. And also we are optimizing the computed, and this is including the optimization process also. Okay, and I'll introduce another development for the solver. implicit matrix solver with improved convergence performance using green function-based neural networks. And so the many studies conducted towards convergence of neural networks and partial differential equation-based nonlinear time evolution problems, but the convergence is not sufficient because of difference in required accuracy of the solution. As I said, that PD solution schemes are very high accuracy but costly, and neural network-based schemes low analysis cost but accuracy is low. So they proposed that approximate green function for the PDE in the preconditioner of an iterative solver. So high accuracy preconditioners green function reflect the properties of PDEs, and scalable large system as preconditioner consists of only local operations. So this is the example of 3D case green function, and high accuracy modes include green function on 3D, and this and we estimate these coefficients using the neural networks, and then high frequency modes are resolved by in high accuracy with only a few parameters shown in the previous parameterization. And then we can, this is a distribution of green function, and this is the difference between the simulation, true simulation, and comparing the neural network estimated by neural network. So very good approximation is achieved. And these performance test results. So convergence speeds are very high. These are conventional solver, and elapsed time is horizontal axis, and these are relative error. And our proposed method is very fast convergence is shown. And also the weak scaling performance is also very good, and this as shown in the right figure. Scaling result is for the 5.57 trillion degrees of freedom problem, the 98.1 week scalability from 800 to 55,000 nodes for and this is 30.3 petaflops, and this is more than 15% of peak performance. It is good, very good for the FEM simulation like this. Okay, so this is the final slide of my talk, and we are in our project. We are doing for the application development for the government and also companies for the long period ground motion simulation, and also tsunami generation. And also we developed the simulation course more suitable for the Fugaku project. That's all. Thank you very much.